Okay. Welcome, guys. So, this video, let's talk about the interesting theorem, and I think seldom people talk about this. So I want to talk about this. Okay. So before I start, I hope you guys subscribe to my channel so you can view interesting mathematics, algebra, geometry, very stupid, strange mathematics, and yeah, in my video playlist. Okay. So now this is another complex analysis video. So one famous result is that this. Okay, so let's maybe first state this theorem. So this theorem says that if 0 to infinity exponential negative x and dx, this is hard to compute. For n greater than or equal to 2, that's denoted this is an. Then the cosine x and dx 0 to infinity cosine pi divided by 2n will be an. This will equal to the cosine this term times this. Okay, so the famous example is that the so-called Fresnel integral, which is a famous cosine x squared dx from 0 to infinity will equals to, let's say, this. I think this one, right? Okay. So so this can be proved by complex analysis, and you can follow my previous video. I will post a link below. Okay, and yeah, so you can directly compute this by complex analysis. But now we can use this theorem, right? So this theorem tell you that use theorem. So theorem tells you that this is a cosine pi divided by 4 times a2, right? A2, which is 0 to infinity exponential negative x squared dx. So this is a square root of 2 divided by 2 times this is what, a half square root of pi divided by 2, right? So yeah, so a simple calculation, you get the same answer, right? So Fresnel integral just a special example of this theorem. Okay, so this video just to prove this theorem. Okay, so let's go to. Okay, so let's see another example. Another example is that if you say that this guy is a3, then you can prove that cosine a3 dx will be this, right? The reason is that this guy is a cosine pi divided by 6. Okay, so interesting theorem. Okay, so let's start a proof. So let's maybe clean the table. Okay, so proof. Okay, so the idea we have is so-called complex analysis, so everyone knows about it. So let's see x and y, and so this is a z. Okay, so let's pick a contour to be 0. Okay, so let's say this is r, and this r, and let's angle to be pi divided by 2n. And then consider f of z to be exponential, let's say izn. Okay, so there's no pole for this function, right? So if you draw integral from a contour, let's say 1, 2, 3, then you will get df dz will be 0. So 1, 2, 3 will be 0. Okay, and so what we gonna do is that we will take r to infinity. Okay, so one example, one calculation I will quickly sketch is that you can prove that when r goes to infinity, this will be 0. Okay, and the reason, you can easily prove by yourself. Yeah, so let's see. So if z equals to r exponential I theta, then this term will be exponential rn, in theta, and cosine. Sorry, dz ri exponential I theta d theta, right? And then if you take absolute value, then this term will be less or equal to. Okay, so since we take absolute value, so we don't care about this. And then we get this. Okay, so you get the r, but you only take the real part, right? So the cosine n theta part is not important. You get minus r n sine theta part, and the 0 to the finite integral, which is pi divided by 2n. And you can prove that this will go to 0 as r goes to infinity. Okay, and the reason is that, I don't want to write a detail, but you know that the exponential rn will decay very fast compared to the original r, right? So easy to prove. Okay, so that means if we take r equals to infinity, then we don't need to care about the second term. Okay, we only care about the first term and third term. Okay, so what is the first term? The first term tell me that just the standard, right? Just the standard integral. So the first term is ixn dx from 0 to infinity, since we already take r to be infinity. And then what is the third term? The third term, the parameterization for the third line will be just z equals exponential pi divided by 2n x, right? But x from r to 0. So since we were from r to 0, right? And since we take r to infinity, so it's infinity to 0. So this term is just let's see. So infinity to 0, so infinity to 0, and the exponential I, right? So zn, right? So will be, so let's see. Zn will be exponential I pi divided by 2x, right? So it's ix n. So will be yeah. So you see a trick. So this term actually become minus x, and the dx, right? So dx give you is dz, right? dz give you, which is 0. Okay, so now we have this term. Okay, so now take the what? Take the real part. And okay, so let's take, maybe we'll take the real part. So this real part will be cosine xn dx 0 to infinity plus, okay, so let's change it to minus exponential I pi 2n, and the real part, okay, so real part of it, infinity 0 exponential minus xn dx, right? So this guy is an, so we don't care, this is an, okay, an. And this term, real power exponential I pi divided by 2n, will be just cosine pi divided by 2n, right? So clearly we have 0 to infinity cosine xn dx. Sorry, because this is so very easy, so I don't want to waste time, but a very beautiful result. Nice. Okay, see you guys in the next video. Hope you guys like my complex analysis series. I will make the, yeah, I already compiled a lot of complex analysis videos, so you guys can check for this if you need help. I usually do it step by step. Okay, see you guys next videos.